And second of all, I don't think we should suppose for one instant that the breaker guys don't want to be faster too. And I think it's actually easier for us relay guys to be faster, quicker than it is for the breaker guys to get there. So I want to be first. I don't like being second or last. So we're gonna get there. There's immediate payoff, and we know circuit breakers are going to speed up too. There's lots of interest in DC around the world, and well, circuit breakers will be developed for medium and high voltage DC, and the benefits of that technology will show up in AC as well. By the way, the techniques that we're talking about here, most of them apply just as well to DC as they do for AC. We say equally fast on 60 and 50 hertz. It should have said 60, 50, 25, 16 and 2/3, and 0 hertz. Here's a picture of a Bewley lattice diagram for a real fault. So here's you were talking about that dress thing. Can you see there's a line there? I can't see it from here, but there's supposed to be a barely. Should be a gray line at the left end of all those yellow peaks. You see it? That's my end of the line. Your end of the line is over here at where these little peaks are showing. There should be another line there. When we go home, we're going to fix this slide so we can see it better on any computer. So what we got here is time's running down the page, and here we are. Here's a point somewhere between me and you. It's pretty close to me, pretty far from you on this line. We might assume to be 100 miles for fun. So a fault occurs right here, and the traveling wave comes and bounces off my bus, goes out, bounces off the fault, bounces back, so I start to see these blips. They don't look anything like 60 hertz, do they? Because they're not. They don't really care what's going on with respect to the 60 hertz. So what's so cool is we can start to use these observations of these blips to tell us how far the fault is. Now another thing that's interesting is this is where the fault occurred, right where the green dot is. We're there. So that's when the fault occurs. So I don't know anything about it until this much time has passed. It's already old news by the time it gets to me. Not quite yesterday's news, but or cold mashed potatoes, but it's old. And it's even older when it gets to you because the fault happened to be closer to me. So, in any case, we can use these relative times of arrival accurately measured at the two ends of the line as a very reliable means of quickly determining where a fault is and if it's in section or not, and come up with commands to trip the breaker. Now, we're going to have to figure out how to test these things in the field, and we got ideas and other people do too. So let's move on to another one, and it's a sobering thought that almost every day somebody in the United States is seriously injured or loses his or her life to arc flash. I think the numbers are getting better finally, but this is something that drives home the point we made initially, that in this day and age there's no reason to wait to clear a fault. So what we do, here's the one for motor protection. You can see there's a little white window right there, and that's a light sensor. And in the case of the distribution relays, you plug some fibers into this thing, and you run the fibers inside the gear. So when there is something dangerous inside something bad happens inside the breaker, you get current and light. So let's take a look at what it's like when this operates in about 5 cycles, where the arc flash relay trips the breaker very quickly. Could barely see it. Still would be scary if you're right there. And I'd love it if we could turn the sound up on this. So here's 46. That would be if it was time coordinated. You want to see it again? Yeah? Show me your hands. See it? Okay, we'll do it again. Here we go. Don't miss the 5-cycle blink. I'd love to turn up the sound for some of these, but there you go. So that's the difference it makes, and you can imagine if it was 1 second or longer. It's a technology that saves lives. And we worked hard to do this for a very low cost, and we think it's something that is already paying off. How's it work? What's cool here's the current, and you can see the fault current jumping up on a couple of phases. And the next trace here shows the light flash, that red line going up. And this yellow line on the middle one, that happens to be where the relay is determining the magnitude of the current. So by the time that there's enough of current and light, put those into an AND gate, and we're getting a trip command to the breaker in 4 milliseconds. So the rest of that 5 cycles was due to the breaker. Is that fun or what? So we have a little gadget that produces the light flash so you can test that. So what about an automation? That with the real-time automation controllers, hey, SCADA is 5 seconds. That's like going to a NASCAR race and opening the shutter of your camera and waiting for all the cars to whiz by, then closing the shutter, going home and developing the film and say, look at the cool picture I took. It's a one big blur. So that's what SCADA is when it comes to looking at the fast dynamics of the power system. One big blur. We got to speed up, so we've got a need for speed there. And we're getting down now to where we can do things in 4 milliseconds or less instead of 5 seconds. So some of the slower stuff like thermal things, well, you don't have to run them as often, and you spread that out over multiple processing intervals. Radios are fast. Just because you don't have a wide area Ethernet network or something doesn't mean you gotta give up speed. In fact, you look here, the serial radio, the 3031 is doing 4.8 milliseconds end-to-end with encryption. Now, Ethernet takes longer because the packets are bigger. And because the packets are bigger, you also lose something in range to get the same signal-noise ratio and a wider bandwidth because of that's the facts of life, okay? But it's still darn good compared to SCADA kinds of speed. We're talking milliseconds and microseconds these days. Another fun thing that we're doing is when you go out to test one of these, people are always worried about what the RF environment is. So you put them in, and you could check it with a spectrum analyzer, which is still a good thing to do, I suppose. But after you get the things set up and running, you can look at a spectral display and just to see how good the signal is and how good the noise is, and if there are any sources of interference, and you can check it whenever you want to. Here's another thing. Let's talk about precise time and the miracle of the GPS satellites. In fact, there goes one now that has given us nanosecond absolute time anywhere in the world. And now We got the blue ones, which are the Americans, and the red ones, which are Putin's. So we decided we'd make a clock that picked up both the American satellites and the Russian Federation ones. So what's cool about that is if a bad guy tries to spoof or jam the thing, he's got to spoof and jam or jam both. And that gives us some means of doing some tests that inside the clock to beat the people who would mess with that. Now, if you don't believe people mess with it, well, you can look up NAVWAR, N-A-V-W-A-R. You can do an internet search for it, and then look at GPS stuff. You'll see that run across the test they did at Fort Bragg. And here's, I was coming back from Monterrey, Mexico last Tuesday, a week ago tomorrow, and we were flying just to the west of White Sands, New Mexico, and there was a NOTAM, a Notice to Airmen, that said GPS would be unreliable in this area. And the pilots told us, yeah, the airliners are all complaining about their GPS not working. That was just last week. So we got to be aware of that, especially when we're testing things and when we're designing systems. So time is part of a system. So what we've worked on is, hey, we got to authenticate time code. And by the way, who's ever looked at IRIB on an oscilloscope? Who knows what IRIB is? That familiar? Okay, it's a time code. What is it? Inter-Range Instrumentation Guide, Standard B, from 1958. So these guys got it right in 1958. We're doing IEEE 1588, the PTP, and it's a lot more complicated than IRIB. All just to save a little cable. You can buy a lot of cable at 10 cents a foot compared to replacing Ethernet switches, but the other world will keep moving on. So here's what we do. I still like IRIB because it's easy. You can test it with an oscilloscope, and does a great job. So, we were getting 1/2 the error, 20 nanoseconds versus 10 nanoseconds. So what we can do is take two sources of IRIB and stick them into this thing, which distributes it to a lot of devices, but it also compares. So let's suppose that one clock is telling you that it's 8 o'clock, and the time quality bits are good, and the other clock is saying it's 7:59 and the time quality bits are good. Somebody's lying. So you raise a flag and let everybody know. So it's a lie detector and takes care of the problem. So here's another way for time integrity. One thing to do is, I think it's a pretty good idea not to stick the antenna in plain sight. So you put it up high enough where maybe nobody can notice it. And that's a first offense. If you've got two antennas, you put them in different corners so it's a little harder for a bad guy to jam them both. And by the way, I'm not being alarmist about this. I'm being practical about it. So here's a GPS clock, and the satellites are hidden. Here's a terrestrial system. The ICON network will distribute precise time within tens of nanoseconds. And if you do lose a GPS, everybody on that network still thinks it's the same time to the nanoseconds, and that's good. So we talked about the IRID authentication, and then the IEDs, the relays themselves, do a quality check. So it's real easy to test clocks accurately. So here's one way of doing it. We use a satellite simulator which puts out a radio frequency signal as well as a reference pulse, 100 pulses per second. And then we can stick that through the RF into the clocks to be tested and watch them. So if you don't have this, which you probably don't, you can still check clock versus clock and they better agree. So here's what it looks like when you hook your scope up to it. And what we did here is we triggered the scope with that reference. So this is top dead center. And here's a 2488 with running on its temperature compensated crystal oscillator.